This lecture is for section 7.2, and we are going to talk about spanning tree and finding the minimal spanning tree using the greedy algorithm. So the topic of spanning trees is motivated by graph optimization problem. So for an example, in figure 1.1, if we find that figure in the lecture, it's talking about 4 different campuses of the Atlantis University, North, East, West, and South. That these campuses are in the Atlantis University system. A new secure communication system is being installed, and the objective is to allow for communication between any two campuses to achieve this objective. The university must buy direct lines between certain pairs of campuses. Let G be the graph with a vertex for each campus and edge for each direct line. Total communication is equivalent to G being connected graph. This is due to the fact that two campuses can communicate over by number of lines. To minimize cost, the university wants to buy the minimum number of lines. The solutions to this problem are all trees. Any graph that satisfies the requirement of the university must be connected, and if a cycle does exist, then any line in the cycle can be deleted, reducing the cost. Each of the 16 trees that can be drawn to connect the vertices, north, south, east, and west, remember that example we talked about in lesson 1, solves the problem as it is stated. Note that in each case, 3 direct lines must be purchased. There are 2 considerations that can help reduce the number of solutions that would be considered. The objective one is, given that the cost of each line depends on certain factors such as distance between campuses, select a tree whose cost is as low as possible. Whereas objective 2 is, suppose that the communication over the multiple line is noisier as the number of lines increases. Select a tree with the property that maximum number of lines that any pair of campuses must use to communicate with is as small as possible to reduce the noise. Typically, these objectives are not compatible. That is, you cannot always simultaneously achieve these objectives. In the case of the Atlantis University system, the solution with respect to objective 1 is indicated with the solid lines in figure 1.1, whereas the dotted line is the solution for objective number 2. So let's go back to the picture one more time. So the solid line represents west to north to south to east, whereas the dotted line represents west to north, whereas west to south and west to east are the other options. So in the first situation, both intermediate vertices north and south has degree 2 and west and east has degree 1, whereas in the second objective situation, west has degree 3 and north, south, and east campus all are of degree 1. So our objective now is to identify a procedure that is going to help us find the spanning tree as a minimal spanning tree, and in this section we will be emphasizing finding solutions to our objective 1. So definition of a spanning tree. So first we will define a spanning set. Let G is V comma E, a connected undirected graph. A spanning set for G is a subset E prime of the edge set. So you're keeping all the vertices, but you are possibly not keeping all the edges, such that B E prime is already connected. So make sure that the graph is connected and delete all other edges, but still keeping the connectedness. That's called a spanning tree. If E prime is a spanning set of the graph G, then T equal to VE prime is a tree, and then T is called a spanning tree for G. So of course, because in this situation the spanning tree is a tree, the number of edges in the spanning tree is 1 shorter than the number of vertices. And the significance of the spanning tree is that it is minimal spanning set. A smaller set would not span the graph, while a larger set would have a cycle which has an edge that is superfluous. For the remainder of the section, we will discuss 2 of the many topics that relate the spanning trees. The first is the problem to find the minimal spanning trees, which addresses objective 1, and the second one is, of course, finding the minimal diameter spanning tree, which is objective 2. So what is a minimal spanning tree? Given a weighted connected undirected graph G, V, E, W, so V is the vertex set, E is the edge set, and W is the weight of the edges, a minimal spanning tree is the spanning tree V, E prime for which the sum of all the weights is as small as possible. So unlike many of the graph optimization problem we examined before, a solution for this type of algorithm is actually pretty efficiently obtained. So let's talk about that algorithm. So we're going to define a concept called bridge. So let G is V, E, an undirected graph, and let L and R, so left and right, be partition of V. A bridge between L and R is an edge in E that connects a vertex in L to a vertex of R. So the theorem states if G is equal to VEW is a weighted connected undirected graph, let V be partitioned into two sets L and R if E star is a bridge of least weight between L and R. So there could be more than one bridges. E star is the one which has the least weight. Then there exists a minimal spanning tree for G that must include this edge of minimum weight. Proof is pretty simple and formal. Suppose that no minimal spanning tree including E star exists. Let T equal to VE prime be a minimal spanning tree. If we add E star to the tree, then we get a cycle. And this cycle must contain another bridge E between L and R. But because the weight of E star is less equal to the weight of E, we can delete E, still get the connection, and we get a new tree, which includes E star as the part of the minimal spanning tree. So example 1.7 describes the bridge. So if we go to that example, we have these oval shapes representing L and R. So in L, we have three vertices A, B, C. And in R, we have two vertices D and E. The bridges are the edge between B and D, which is of edge weight 4. And the other bridge is the edge between C and E, which is of bridge weight 5. So in this example, the bridges between the vertex sets ABC and DE are BD and CE. According to the theorem above, the minimal spanning tree that includes BD must exist. So any minimal spanning tree if you're thinking of, it must contain the bridge of minimum weight, which is 4 here. So it must contain B and D. By examination, we should be able to see that it is true. But is it true that only the bridge of minimal weight can be a part of the minimal spanning tree? So think about all the minimal spanning tree in this graph. I know that 4, the weight 4, which is the edge BD, is going to be a part of that. Does that mean that CE is never going to be a part of this minimal spanning tree? And we're going to answer this question as one of our exercises in this chapter. So before we go there, let's talk about the algorithm, which is called Prim's algorithm, and it's one of the nicest and most efficient algorithm in order to find a minimal spanning tree. So what we do, let G, V, E, and W be a connected weighted undirected graph, and let V naught be an arbitrary vertex in V. So choose an arbitrary vertex. The following steps lead to a minimal spanning tree for G. L and R will be sets of vertices and E prime will be a set of edges. So initialize, call the left set as V minus V naught and the right set as only V naught, and in the first step we have no edges. Now we're going to build a tree, and how do we do that? L, if it is not equal to the empty set, then find the E star, which is a bridge between L and R, with minimum weight between L and R. If you have multiple of them, select one. Then you change your R by including VL, which is the source of this edge, and you subtract VL from the left set. And you say your new E prime is whatever E prime was in the previous step, along with this bridge E star. and we will terminate with a minimal spanning tree by repeating step 2. So I'm going to show you example, and this process is going to be very clear to us. But before that, let's talk about the note. So note 1.10 says, if more than one minimal spanning tree exists, then one that is obtained depends on V0, and the means by which each star is selected is in step 2. So I can get more than one minimal tree. The warning is, if two minimally weighted bridges exist between L and R, do not try to speed up the algorithm by adding both of them. Select one. The algorithm 1.9 yields a minimal spanning tree. It can be proven by induction with the use of theorem 1.6 in this section. And it is not known whether this algorithm works if we start with a not connected tree. If a connected tree is there, then this algorithm works, but with a tree which is not essentially connected, this algorithm might not work. So the small example that we have is a graph. It's clearly a connected graph, and I'm going to go ahead and do the algorithm work with you on this example. So remember, I can start with any vertex and call it V0. So what I will first say, let's determine a vertex, and I always prefer to start with the vertex A, the least possible leveling. So I'm going to say L is the graph, so the entire vertex set of the graph, minus the vertex A, whereas R is only the vertex set A, and E prime is the empty set. There is nothing at this point. So this is my step 1, and I'm going to repeat step 2 multiple times and show you the changes in my L and R. So think about R. R is your vertex A, only A. You are trying to find the bridges between A and the rest of the graph. So there are two bridges, 6 and the weight 3. So of course 3 is the lower weight. So I'm going to go ahead and choose this weight. And what it does, I'm going to now say that my new, in step 2, my new L is going to be whatever I had already. So you already had V minus singleton A. You're going to now delete A from it as well. Whereas R has become, it was A, now you have added the edge F to it. So now the set R is the vertex A and the vertex F, and you are looking for all the bridges between these two vertices and the rest of the graph. So how many bridges I have? Well, I have this one here, I have this one here, I have this one here, and I have this one here, and I'm finding the least weighted bridge. Of course, that's 4, so I can forget about these 3 edges and keep this one. So step 2, part 1 has given you a new L and R. Now step 2, part 2 is going to give me a newer L. So now I'm going to call L to be the vertex set minus the edge AF, and we have added E in the subtraction list, whereas R is going to be the set A, F, E. And the one thing we did not do last time, we did not talk about what is the set E prime. Remember, E prime was the empty set. Now you have one edge in step 2, part 1. And the edge is A, comma F. This is my edge. I can write it this way. And now we have 2 edges in my E prime after step 2, part 2. So the edges are, we already have A, comma F. And now we have the edge F, comma E. Okay, so now you have R consisting of A, F, and E, and you're looking for all the connections. So let's see what are the connections between these 3 vertices and the rest of the graph. So I have these coming. So this is no longer a connection between F and E, because F and E are part of the same partition. But I have this one, I have this one, I have this one. So what we will do now, we're going to choose the least possible weight. So the weights are 6, 6, 6, 3, and 3. I have 2 minimum weights of 3. simply choose one. Doesn't matter which one, choose one. So let's say, for example, I choose the edge between E and D. It does not matter. I could have chosen between E and C. So now, after we have done our step 3, the set L has now become D minus A comma F comma E, because we have selected D. I would say D there. And the set R has become one more here. So A comma F comma E comma D. And similarly, we're going to write down the changes in our edge set. And that is going to be, so now we have 3 edges in this. AF, FE, and we have ED. So we're looking for connections again. So now we are looking for connections between AFED, this is one part of the graph, and I want to find the connection between the other parts of the graph. So what we will do, we will try to find the bridges. So again, see, this one is a bridge, that is a bridge, this is still a bridge, this one is a bridge, this is a bridge, and that's about it. So it is pretty obvious that we're going to choose the bridge between D and C, so the rest of them can go away, and accordingly we're going to change our L and R and E prime. So let's see, after step 4, I mean step 2 part 4, my L is B minus A comma F comma E comma D comma C, whereas my R has become A comma F comma E comma D comma C, and we will say E prime is the set of AF, FE, ED, and DC, and we will repeat. So now we have AF, ED, and C part of my partition R, and partition L is the other two vertex, B and G, and we're looking for all the bridges. So the bridges are this edge, this edge, this edge, this edge, this edge, this edge, and this edge, and you are finding the smallest possibility. So I see that the edges you can find now for the smallest possibility can be twofold, because the smallest, the smallest number is 3. It's between E and C. I'm so sorry, E and C cannot be, because C is the part of. So let me do the bridges one more time. I made a small mistake in this thing, so I want to go back and do it one more time, just identifying the bridges. So the bridge is between A and B, F and B, F and G, E and G, but E and C cannot be a bridge. So C and B and C and G. And as you can see, I have a twofold choice in front of me. The minimum weight is 5. I can either choose between F and B, or I can choose between C and G. One of them. I can choose between F and B, or I can choose between C and G. So let's just choose between F and B. So if I choose between F and B, because that's a minimum weight, I will get rid of the rest of my options. And in this situation, we will write down L, R, and E prime one more time. So L in part 5 is going to be V minus A, F, E, D, C. And remember, I included B in this list. So R is going to be A, F, E, D, C, and B. And E prime is the set of edges, so it was AF, FE, ED, DC, and now we have the edge BF or FB, whichever way you want to write it. because these are undirected. It doesn't matter whether I write BF or FB. So that's my new A set. So to get the minimal spanning tree, I still need the connection. So G is not connected with this graph yet. So now I'm going to find all the bridges between my graph, between the left set of G. So G is the only element that is left and it should be connected. So the only bridges that I see between G and the rest of the graph are these 5 sides. And see, the least possible weight that you can select is the weight 3 out of this 4. So I'm going to select that, and that has completed my problem. So I will go ahead and do it as we were instructed. We will now write down L. Remember, we included G, so this set has become empty now. And R has become all these vertices, A, F, E, D, C, and B. And the set of edges has become AF, FE, ED, DC, BF, and finally we did BG. So that's all my edges. And this has given you precisely the minimal spanning tree. So what is the minimal spanning tree? What I will do, I will just draw on this graph the edges that I have selected in the set E prime, and that will give me an idea for what is the minimal spanning tree in this situation. Okay, so we started with AF, so that is considered. Then FE, then we did ED, then we did DC, then we did FB, and finally we did BG. So if I have to draw that separately, I will say A goes to F, F goes to E, E goes to D, D goes to C, F goes to B, and B goes to G. A, F, E, D, C, B, and G. And what is the cost of this list minimal spanning tree? Remember the costs individually. This was 3, this was 4, this was 3, 2, this is 5, and this is 3. So how much I get? I add all these weights. So 3 plus 4 is 7, plus 3 is 10, plus 2 is 12, plus 3 is 15, plus 5 is 20. So the minimum cost is 20. And this is, again, don't make that mistake, this is the least possible weighted spanning tree, but it is not unique. I can have more than one choices for this. If I go back to the example that the book has done, the same example, in their identification, they have chosen the exact same minimal tree, AF, FE, EC, CD, FB. Actually, they took EC. And see, so this is a different minimal tree that they have. So in the book, the minimal tree that they have done AF, then they have done FE, then they have done EC, they have done CD, and they have done FB, and they have done BG. As you can see, the only difference is the edge between E to C and the edge between E to D, but both of them are weighted 3, so the minimal cost is still the same. And you have multiple different answers for each of these problems. All right, so that is the algorithm. It's pretty simple and pretty efficient. And what we will do in practice, we're not going to write down L, N, R, and E prime over and over. We're going to kind of trace the minimal spanning tree as we are progressing through the steps of the algorithm. Okay, let's carry on. And we're going to talk about the minimum diameter spanning tree. Even though we are not going to spend much of time or do any exercise involving minimum diameter spanning tree, but we need to understand this is the concept that answers objective 2 in our quest. So given a connected undirected graph G, V comma E, Finding the minimum spanning tree of G such that the longest path in the tree is as short as possible is called the minimal diameter spanning tree. So in case of a complete graph, the minimum diameter spanning tree problem is trivial to solve in Kn. Select any vertex V0 and construct the spanning tree whose edge set is the set of edges that connect V0 to the other vertices in Kn. So as simple as if you start with V1, you just choose the edges that connect V1 with V3, connects V1 with V2, connects V1 with V4, and connects V1 with V5. And that will be the minimum diameter spanning tree. For other types of graphs, finding a minimum diameter spanning tree is more or less a question of intricacy. And we're not going to spend much of time on that. So let's go ahead and start working on the exercises on this section. So the first one was the question that was raised in the example of bridge problem. The question was, we know that in a minimum spanning tree, the minimum weight bridge is always going to be a part of. But does that mean any other bridge will not be the part of the minimum spanning tree? The answer is no. In order to explain this answer, let's try to concentrate on this graph. So this is a graph that I thought about. I already have set my left set and right set. The two vertices in the left set are 1 and 4, and the two vertices in the right set are 2 and 3. And you see the two bridges between left and right. The two bridges are 5 and 10. Of course, 5 is the lowest weight bridge, so any minimum tree is going to contain that. But does that mean 10 is not going to be a part of the minimum spanning tree? Okay, so let's try to think in this way. Say we are connecting R to L, and we already said that the minimum spanning tree is going to contain this length, 10. Now connecting L to R, we're going to choose the minimum weighted bridge, so we must choose this bridge. Now, in order to connect between 3 and 1 and 4 and 2, you are going to look for all the bridges. So the bridges are 10 and 15. These are your two choices. Which one is the minimum one? That's 10. So you're going to choose that bridge to be the part of your minimum spanning tree. So the minimum spanning tree in this situation is 1 to 2, 1 to 4, and 4 to 3. And see, both bridges, 5 and 10, even though 10 is not the minimum weighted bridge, is the part of the minimum spanning tree. So that answers our first question. The rest of the lecture note, we're going to answer questions using Prim's algorithm. So we're going to find minimal spanning tree for the following graphs. So this graph is pretty simple. It has 6 vertices, numbered 0 through 5. And let's start with our right-hand set to be singleton 0, and rest of the graph is the left-hand set. And as I said, I'm not going to write left, right, and the edge set over and over. I'm just going to mark the edge that I have considered to be the minimum weighted bridge. So as I said, 0 and the rest of the graph, the bridges are 4, 5, 6, 5, and 4. Choose the minimum weight bridge. There are 2 4s, doesn't matter which one. I will choose the one that connects 0 and 5. So what I do now, because I have chosen this edge in part of my minimum spanning tree, I'll just redraw that. Then I have connection between the part of the graph which consists of 0 and 5 and the rest of the graph. So what are my bridges? You have this one as a bridge, you have this one as a bridge, this one, and this one. Again, the minimum weight is 4, so you choose the one that you like. I have 2 4s. Let's just choose the one that is between 5 and 4. So I'm going to keep this. And now we're going to choose the connections again. So the bridges now are 8, 6, 5, and 4. So see, the minimum bridge is weighted 4. So keep that as your edge in the minimum spanning tree. So now we're going to connect 0 and 1. So now we have new sets of bridges. So we have 5, 6, 5. We have 4 and 8. So the minimum weight is still 4. So I'm going to delete rest of the bridges and keep the one with the minimum weight. So we'll get 1 to 2 now connected. So we have again new set of bridges. We have this, this, and this. Clearly the minimum weight is 5. And see, if I add any of these sides that are of weight 5, then I'm going to get a cycle. And why this situation is occurring? Because considering those two 5 is not actually a bridge between the graph in R. What are the vertices in R? The vertices in R before this the step that we started was 0, 1, 2, 4 and 5. And the only other vertex was 3. So I was trying to find a connection between 0, 1, 2, 4 and 5. But if you think about the weighted 5 bridges, their connection between 0 and 2. So they should not have been included in our initial quest of finding minimal connections. So be a little careful about this. So these are your only 3 bridges between 2 and 3, 4 and 3, and 0 and 3. So the minimum weight is 6. So I'm going to keep that and get rid of the rest of them. So the minimal spanning tree is now found. And the minimal spanning tree is of the form 0 connected with 3, 0 connected with 1, 1 connected with 2, 0 connected with 5, and 5 connected with 4. And you can find the lowest cost. These costs are 4, 4, 4, 4, 6. So the total cost is going to be 4 plus 4, 8, plus 4, 12, plus 4, 16, plus 6, 22. So the cost of the minimal spanning tree is 22. Answers your question. So let's go to next example. Again, you are trying to find out the minimal spanning tree. So this graph is certain American cities and the connection with the other cities, and we want to find out the minimal spanning tree. And we can start at any city. So let's just start with San Francisco. The only connection between San Francisco and the rest of the cities are San Francisco to Los Angeles and San Francisco to Chicago. Of course, the connection weighted 50 is the least one. So let's choose that. I'm going to choose San Francisco to Los Angeles, which is the weight 50. And then I have Newark connection. So this is still a connection. That is a connection, this is a connection, and the least connection is between Los Angeles and Kansas City. So let's go there and mark it. Now the connections are, I still have the connection between Los Angeles and Chicago, San Francisco and Chicago, Kansas City to Atlanta, Kansas City to Philadelphia, Kansas City to Chicago. So of course the connection between Kansas City and Chicago will stay, and rest of them will go. So this is my Newark partition now. I have 4 cities in this partition. So what are my connections? The connections are this, 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 this. And see, the least connection between all of these possibilities is Kansas City to Philadelphia. So we'll connect that. Kansas City to Philadelphia is my connection. And my Newark connections now are going to be Chicago to Boston, Chicago to New York. Chicago to Philadelphia is no longer a connection, but Philadelphia to New York, Philadelphia to DC, and Kansas City to Atlanta is your connection. The least possible connection is between Philadelphia and New York. So we'll keep that and mark it and look for Newark connection again. So now we do not need the connection between Chicago and New York. But Chicago and Boston is good. New York and Boston is good. New York and DC is good. Philadelphia and DC is good. Kansas City and Atlanta is good. So again, the least connection is between Philadelphia and DC. So we'll keep that and get rid of the rest of them. So Philadelphia to DC will be connected with the connection of 35. And I look for my connections now. The connections are going to be Chicago to Boston, Kansas City to Atlanta, Boston and New York is a connection, New York and DC is a connection, and that's pretty much it. And the minimum connection is between New York and Boston, so keep it. New York and Boston is connected. So as soon as we have done that, my choices for connection has reduced dramatically. So what are my connections now needed? Well, see, I would like to find a connection between Kansas City and Atlanta, because Atlanta is the only city that is not connected in this mess already. So there is only one path left, and we're going to connect Kansas City to Atlanta. And we found our minimal spanning tree. So how does it look? It looks San Francisco to Los Angeles, Los Angeles to Kansas City. Kansas City has a bunch of connections. It goes to Chicago, it goes to Philadelphia, it goes to Atlanta. Philadelphia has a connection to DC, it has a connection to New York, and New York has a connection to Boston. So the point is, I have included all my major cities, I still have a tree, and that is the minimal spanning tree. And as usual, if you add all these numbers that are labels or the weights of these edges, then you get the cost for the minimal spanning tree. We have one more example of this type, we'll finish it. And this example is again a connected, unrelated graph, which we are trying to find the minimal spanning tree for. And there are 8 vertices in it. So let's start with 1. And as usual, we're going to find the minimum bridge between 1 and the rest. So your bridges are these 3 only. So I will choose between 1 and 8 and make it a bridge. Then my bridges are between this, 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 and this. And the minimum weight is 4. So keep that. And connected. So now we have 1, 8, and 2 connected. So the bridges looking forward are 10, 4, 2, 6, 11. Of course, 2 is the least one. So I'll keep that and get rid of the rest of them. So I go 2 to 7. My connections are now 4, 3, 4, 10, 6. 6 is not needed because this is part of the actual partition already, and 11. Well, 3 is the least one, so keep 3 and get rid of the rest of them. So I go 3. So now one partition already have 1, 8, 2, 7, and 3. The rest of the graph is just 4, 5, and 6. So I'm looking for the connections. These 2 are still connections. I have newer connections, and these connections are 6. I also have connection 4 here. And that's pretty much it. So the least possible value of the connections is the 4. So I will get rid of the rest and connect 4. And then we have to connect 2 more vertices, and those are 4 and 6. So I have 11, 10 still their connection. You have this 6 as part of your connection. You have this 4 as a part of your connection, and you have this 6 as part of your connection. And the least is, of course, 4. So we'll get rid of the rest of them and keep 4. So I have the connection between 6 and 4. That's the newest connection. And then the only vertex that should be added is 5. So I don't have many choices. I have only one choice. So I'm going to go ahead and connect it. And that is the minimal spanning tree. So what I have 1 going to 8, 8 going to 2, 2 going to 7, 7 going to 6, and 7 going to 3, 6 going to 4, and 4 going to 5. So if I want to know the weight of this minimal spanning tree, then I will just add 2 with, so this was, I believe, was 4, yeah. So 4, 2, 3, 4, 4, 2. So it is 2 plus 4, 6 plus 2, 8 plus 3, 11 plus 4, 15 plus 2, 17. So the minimum cost of the minimal spanning tree is 17. So the process is fair and very simple but very efficient. And your homework problems are mostly consisting of problems where you are going to be given with a graph and you have to find out the minimal spanning tree. And more precisely, I would ask you to write down the cost of the minimal spanning tree.